Welcome students. In this week's video, we are going to talk about the the Kirchhoff's formula, but for higher dimensions. So essentially, we want to solve this equation, right? UTT minus Laplacian of u equals to 0. So as we have seen that once you can solve the homogeneous problem, you can use the explicit formula to construct a solution for the inhomogeneous problem via the Duhamel's principle. So here this is the problem we are interested in. So this is in Rn cross 0 infinity, right? And we are just assuming that u at the point x0, this is, let's say, g of x, and ut at the point x0, let's say that is h of x. Clear? Okay, so basically at the base time t equals to 0, we are assuming that u is g and u with respect to t is h. Now what is our aim? Our aim is to find an explicit solution, find an explicit formula okay, u in terms of g and h, right? So this is one. Now as let us just quickly recall just once that what are the formulas that we have obtained till now. Yes, so the first formula which we have often, so we saw that if we really want to do this thing, you can't just go about it in a straightforward way. What we need to do is first of all find a formula for n equals to 3, and then with the help of the method of descent. So for what we did up till now is this. So let's put a small revision in here. Okay, so for n equals to 1, what we did is we derived the D'Alembert's formula, right? Alembert's formula. Okay, so for n equals to 1, so the n equals to 1, essentially what is the equation then? UTT minus uxx equals to 0. That's the equation, right? And we have D'Alembert's formula, which gives you an explicit formula for u in terms of g and h, right? So for n equals to 2, what is it? It is called the okay, n equals to 2, we did that, but initially, so we started for, let us first write it down. N equals to 3, yes, we had the formula which we called as the Kirchhoff's formula, right? I am not writing all that because you guys, it's already done. Yes, and for n equals to 2, with the help of Kirchhoff's formula, so, and of course D'Alembert's formula. Okay, so here's the deal. You see, first of all, for n equals to 1, we proved the D'Alembert's formula, right? Yeah, you can do it in two methods. We did it with the help of two different methods, right? One is the method of characteristic, and another one is the method of canonical form. Okay, so once you have the D'Alembert formula for n equals to 1, you use that formula to construct a new form equation. You remember that Euler-Poisson-Darboux equation, and with that formulation we formulated the Kirchhoff's formula for n equals to 3. Right, now from there, with the help of method of descent, we actually got for n equals to 2, so it is called the Poisson formula, right? Poisson formula. Okay, so this is via method of descent. Okay, I am descent. I am always getting this wrong. Okay, so is it clear? What did we do? N equals to, first of all, this is the first step we took, n equals to 1. This is the second step we took, n equals to 3. And so from here to here we went n equals to 1 to 2 and 1 to 3, and then we went to from the method of descent we went to 3. Here what we want to do is we want to do it for a general n. Okay, for general n in n. Clear? Okay, now we are going to see the idea is this. We are going to use the same sort of idea what we did here. Okay, Kirchhoff's and Poisson formula, the same sort of thing we are going to do, just in a in a context of a general n. Yes, so the formulas are going to get a little bit more dark if you want. Yes, I mean they are more complicated. Let's put it like that. Yes, and that's all. I mean, they're just a bit complicated, but the ideas hold exact same sort of ideas. Yeah, nothing much. Okay, so let's do that. So for first thing first, I'm going to write down some identities. Okay, so first of all, you guys know the deal. First thing first, we have to find out the solution for n odd. Okay, n odd. A naught, I mean, and here so n is equals to 3, 5, so essentially n is greater than equal 3, of course. Okay, n equals to 3, 5, 7, whatever. Yeah, n odd. I mean, if you want, you can just take it to be 2k plus 1. Okay, and k is greater than equal to 1. You can think of it like this. Yes. Okay, and for that, let me write down some inequalities. I mean, identities. Sorry. So some identities. Okay, so these are some useful identities which we are going to use. So let phi from R to R. So basically I am looking for a ck plus 1 function from R to R. Okay, and then for k equals to 1, 2, it goes on like this. These particular things hold. Number 1, d2 dr2, okay, of this particular thing. See, these are some identities. This has nothing to do with any PD or anything. Yeah, for any phi which is in ck plus 1, so k can be 1, 2, whatever. Yes, so you take I mean, for example, you take a c in Rn, let's say, yeah, R5 or R8. So I mean, you can have this formula. That's what I'm trying to say. Okay, 1 by R ddr of power k minus 1. So basically this multiplied k minus 1 times. Okay, to r to the power 2k minus 1. Yeah, I mean it is not like it is coming from heavens. Okay, this has some I mean, when we do the calculations, you will see that we need this sort of things. That is why we are just doing it beforehand, so as to avoid any complication during our endeavor. Okay, so here this is the formula which let me write it down. Del phi del r acting at r. Clear? So essentially what am I saying is you have r power 2k minus 1 times phi of r, that if you take the action of this particular thing, I mean 1 by r del r, you take the k minus 1 times. Okay, and you take I mean, you evaluate it on this r2 power 2 minus k minus 1 phi of r, and then you take the d2 ddr2 of that whole thing. That will be 1 by r ddr whole power k r to the power 2k d phi dr whole power r. Okay, yes. So please remember this thing, and let me make it very clear. In the examinations or in any other place, I mean in near future also, even if you are going for a research also, do not worry, no one is going to ask you this formula. Or I mean, if you, of course, in research, if you need this something like this, you can always consult your book. Okay, so no need of remembering all these formulas. Okay, no one in their right mind is going to ask you to I mean, you realize this. I mean, of course, you can I mean, you should prove it. Yeah, I mean, all of this can be proved by induction. What I am trying to say is, I mean, this is not a very good idea to put it in some exam or something. Yes, I mean, it does not serve any purpose. That's what I'm trying to say. Okay, so I mean, of course, this is never a part of any exam. This is just some identities which we use to get whatever we want. I mean, to get the Kirchhoff's or the Poisson formula for higher dimensions. Yes. Okay. So now the other identity which we have is 1 by r ddr power k minus 1 r power 2k minus 1 phi of r. Okay, this is equals to summation j equals to 0 to k minus 1. Okay, beta kj, okay, and r power j plus 1 d j phi by drj of r. Clear? Okay. Here these beta kj's, they are constants. Okay, beta kj. Okay, so this is for j equals to 0, 1, k minus 1. They are constants, independent of phi. Okay, so again let me emphasize these. I mean, this may look, that what crazy things are these. This looks crazy, let's be very honest here. Okay, but I mean, these are just some identities, results which we are going to use in our proof. That's all. Yes, I mean, there is nothing special about it, just some calculations which you can, I mean, if you want. Yes, I am not emphasizing that you do that, but because I mean, these are true. I mean, let's just put it that way. Yeah, but if you want to be rigorous, what I want you to do is you can check using induction. So you can use induction and check these formulas. Okay, number 3 is this, that what are the beta k 0. Okay, 0 with respect for, so basically for j equals to 0, so this is 135 dot 2k minus 1. Clear? Okay, so these are the 3 identities. Again, I am emphasizing it again and again. This will never be asked in any SANE examination. Okay, and SANE is here, what I meant is in any real examination, they won't ask you to prove this sort of identity. I mean, there is no point of doing this thing. Yeah, this is just for our use. Okay, now let's look at the proof. Yes, let's look at the proof of the theorem. So essentially, again, as I told you, we are going to do the exact same thing what we did in the earlier cases. Okay, in the notations which I am going to use is this. See, so let small u, okay, small u of xt, clear, be the solution of 1. Okay, so we are assuming that. Is that clear? I mean, I am assuming that small u, see, this is our 1, right? I am assuming that there is a solution. Now I want to find out if I mean, what is the the exact explicit how do I put it, formula for that. Yes, so let u be the solution of 1. Yes, and u is in, where is it, c k plus 1. So I am assuming this thing. Yes, Rn cross 0 infinity. Okay, so I am assuming our small u is at least k plus 1 times continuously differentiable. Okay, now you see what am I doing is I am going to write down new functions. Okay, you remember we defined now, and so recall we have defined a capital U, right? If you remember, we recall, okay, that for x in Rn, t positive and r positive, define capital U of x r comma t. This is given by the average of del b xr u of yt dsy. Clear? Okay, so essentially this is that's the average of u over the sphere del b xr. Yes, I mean, we have looked at this last week, right? And of course, capital U, I mean, you do realize that capital U is definitely in ck plus 1. It's in fact in ck plus 2. Okay, but I mean, of course, with respect to R and T, yeah, and capital U, you can see that it is ck plus 1 with respect to R and T, right? Yes, so that is always there. Okay, now what we do is we write in one dimensional cases, sorry, not for one dimension, for k equals to 1, so essentially n equals to 3 case, okay, u tilde of rt, this was defined as ru, if you remember. Yes, here I am defining it to be 1 by r del r whole power k minus 1, okay, r power 2k minus 1 u of xrt. Clear? So here you see, if you put k equals to 1, you can see that it is essentially ru, r capital U, yeah, r capital U, and of course this is not there. Yes, so this is just an higher dimensional analog of whatever we did in the last week, okay. And of course, what is g tilde of r? G tilde of r is defined by 1 by r del r whole power k minus 1 r to the power 2k minus 1 and the capital G of x r. Clear? Okay. So again, this is exactly the same thing, just in a higher dimensional analog. Okay, for k equals to 1, you realize that it is basically r times g. Again, h tilde of r also similarly you can define exactly the same sort of thing, 1 by r del r whole power k minus 1 r to the power 2k minus 1 h of x comma r. Clear? Okay, so exactly the same thing. Here r of course is positive and t is greater than equal 0. That is given. Yes. Okay. Now you can see that u tilde, so it's a small note, yeah, I'm not writing it down. U tilde of r0, that is going to be g tilde of r, okay, and similarly u tilde t, u tilde with respect to t, the derivative of u tilde with respect to t at the point r0 is going to be h tilde, okay. So that is always there, I'm not writing all that, okay. Now what did we do? You remember, first of all, what did we do? We took this small u, we assume that there is a small u, and we defined this capital U like this, which is the average over the spheres, average of small u over the spheres, right? Now what we did is we defined u tilde, g tilde and h tilde. So essentially we defined u tilde as r times capital U. Yes, and we showed that u tilde satisfies, if you remember, that particular one-dimensional wave equation, right? Okay, so let me write it down. Here also something similar happens. Okay, maybe I can do it in the next page. So u tilde, this is the first lemma, you can say u tilde solves the one-dimensional wave equation, right? So u tilde of tt minus u tilde of rr is equals to 0 in r plus cross 0 infinity. Clear? Again, what are we doing here? See, this is, we are not doing anything special. It's just some change of variables, right? We are constructing functions in such a way that we can reduce everything to one dimensional, use our D'Alembert formula, and then you can have your explicit thing, right? That's what we are doing, that's all. Okay. Again, u tilde is essentially g, that's what we just discussed. Ut tilde equals to h, okay. I really do not have to, g tilde and h tilde, I do not have to, that's easily seen, right? Okay, this is on t equals to 0, right? R plus cross t equals to 0. Clear? And u tilde, okay, that is equals to 0 on r equals to 0 cross 0 infinity. I hope that is clear, right? When you take r equals to 0, you can check that u tilde is definitely going to be 0. So there's, that's a easy observations. Okay, so this can be easily observed. At least these two. Okay, I need to check whether this is true or not. Last time we have seen that this is true, but here we have a special, a little complicated one. So let's just take that part. Okay, so first thing first, proof. So essentially, of course, our R is positive. I mean, there is nothing we have always assumed. See, R is positive assumed, right? So because we are defining if R is 0, I mean there is nothing is basically 0, right? Okay. So at R equals to 0, we have capital U is 0. So yeah, but so R is always positive. We are just assuming that. So proof. You see, U tilde of RR. This one I need to calculate. It is del 2 del r square, clear, of 1 by r del r of k minus 1 r power 2k minus 1 capital U. Right? What am I doing? I am not doing anything except I am just writing it down. See, U tilde, what is U tilde? 1 by it, this is U tilde, right? See, let me put it this way. What is U tilde? 1 by r del r whole power k minus 1 r to the power k minus 2k minus 1 U. This one. Clear? I am taking twice derivative here. U tilde with respect to, del 2 U tilde del r square, right? Okay, so that is why del square del r square of U tilde. Clear? That is what I am just writing it down. Now, you see, this particular thing, if you use this lemma here, that crazy looking lemma, this lemma, okay, you see d2 dr2 of this particular thing, yeah, this is what I wrote, that is 1 by r ddr whole power k r to the power 2k d phi dr, right? Okay, so I'll just write it down here. So that will look like 1 by r del r of k, okay, r power 2k capital U r. Clear? Yes. See, essentially this is the exact same thing. Del 2 del r2 of this particular U tilde, okay, is 1 by r this. This is what you see, d2 d r2 of this is U tilde, right? That is equals to, so this is for any phi, so I can just substitute phi with capital U here in our case, and it is 1 by r del r whole power k r to the power 2k d phi dr. You see, 1 by r del r whole power k r to the power 2k U r, right? Okay. So now you see this is 1 by r del r whole power k minus 1, and then you have r power 2k minus 1, okay, r power 2k minus 1 and U r r. I'm just taking the derivative. I mean what I'm doing here is this. So this is del r whole power k minus 1 and then 1 by r del r. So I'm just breaking one of them and making it to act on this particular r power 2k U r. Clear? So it becomes r to the power 2k minus 1 U r r plus 2k r 2k minus 2 U r. Clear? Yes, that's what I'm getting. Now that is going to be 1 by r del r whole power k minus 1 r to the power 2k minus 1. I can just take it out. It becomes capital U r r plus n minus 1 by r capital U r. Okay, this is for n equals to 2k plus 1. Okay, I can just write it down, right? I mean, in this k, you just replace 2k with n minus 1 by r, right? Yes. Why do I need to replace this thing? Of course, I mean, we are assuming that this is for the odd case. Yeah, you remember n is 2k plus 1. Okay, so we assume this thing somewhere, no? In the initial case, I wrote it here. N equals to 2k plus 1. So basically for 3, 5, 7, all that sort of thing. Yes. Okay. So that is there. So you just replace 2k with this thing and you have this. Now this is our familiar equation, right? You remember this one? Small u. What does small u do? If you remember small u, since capital U, not small u. Capital U satisfies the Euler-Poisson-Darboux equation. Okay. One has this particular thing is equals to 1 by r del r whole power k minus 1 r to the power 2k minus 1, and this particular thing is utt, right? You remember this Euler-Poisson-Darboux equation is utt minus urr plus minus n minus 1 by r ur, that is going to be 0 in the domain, right, inside the domain. So basically this is equals to utt. I'm just replacing this thing. Now what is this? I mean, if you just look at this formula, this is nothing but utt tilde, right? I mean, u tilde is essentially this, right? And if you take the twice derivative tt with respect to tt, then it becomes this. I mean, there is nothing special about it, right? I mean, it's just a definition. You can use the definition and just write it down. Clear? So what does u tilde do? U tilde solves. So therefore u tilde, let me put it here, u tilde solves the 1D heat equation, right? 1D, sorry, not heat, wave equation. Wave equation. Clear? It solves the one-dimensional wave equation. Okay. Now, again, as I told you, these two things you can easily check. I mean, there is nothing special going on here. So you guys please check this part and you are done. Okay. So now what do we have is this. See, this particular lemma, actually if you have something like this, then you can write u tilde in terms of g tilde and h tilde, right, by D'Alemberts. You remember that the half space we did that reflection thing, yes? Okay, so we'll do the exact same thing here. Okay, so therefore for 0 less than r less than t, okay, u tilde of rt, please remember this thing, we are not doing it in the whole. So essentially this is defined here, this is defined here, right? Because r is positive, this is r, this is t, r is positive. Okay, now we are taking that we did that reflection thing, right? If you remember the rod reflection thing, and we calculated it in the whole domain and used D'Alemberts, right? And from there we calculated two different formulas. I'm just using that particular thing. So r is between 0 and t, u tilde of t, it will look like half g tilde of r plus t minus g tilde of t minus r, okay, plus half t minus r to t plus r h tilde of y dy. Clear? This is by D'Alemberts, right? D'Alembert. Okay, now of course this holds for any r in r and t positive, yes, that's there, yeah. And also you see u tilde, u of xt, if you remember, that is essentially limit r tends to 0 capital U of x rt, yeah. If you remember, you see that's the average, right? Capital U, where is the yeah, this is a capital U, right? Now if you take r tends to 0, we have seen this. I think this is a part of assignment in the Laplacian assignment that some week, yeah, I don't remember exactly, but I mean in one of the assignment problems you have seen that limit r tends to 0 capital U, if you take that, will go to this small u of the center here x t, right? Yeah, t is fixed, I mean for any t that happens. So essentially this is true. Okay, now now what we are going to do is, you see, u tilde of rt, then, yeah, u tilde of rt, that is essentially 1 by r del r of k minus 1, okay, r to the power 2k minus 1 capital U of x r comma t. Clear? Okay, this I am now, what I am going to use here, I am going to use this particular the second part 1 by r del r whole power k minus 1, okay, r to the power 2k minus 1 phi of r is this sum, okay, this a little crazy looking sum. So let's just write that sum here. Okay, so this is nothing but just the calculation part, yeah. J equals to 0 to k minus 1, okay, b kj r to the power j plus 1, okay, del j del rj of capital U x r comma t. Clear? So that's your this is from that lemma, right? This is from this identity. Maybe let me write it like this: I1, I2, I3. Okay, this is from identity. So I am taking I2 here. So from I2, clear? From I2. Now what happens is, once you have something like this, I need to do some more calculations. So let me bear, please bear with me here. So here, this, if I want to write it down, okay, this is basically beta k0 r u. Okay, so that is if you want to write it down, this is this is capital U of r x r t plus b k1 r square capital U r x r t plus, and this goes on, right? It becomes bk and j equals to k minus 1 r power k, and you have u r k minus 1, right? So it is del k minus 1 by del r k minus 1, so k minus 1 time derivative, okay, capital U of x r comma t. Okay, so that is your U tilde. It's a little big expression. I just broke it up and I wrote it like that. Okay, so now look at this thing: b k0 r u of x comma r t. Yeah, this expression, this can be written as U tilde of r t minus this whole thing. Yes, I don't know if I want to write it down. Let's say this particular thing, yeah, let us call it as some pi, okay, capital pi. I'm not writing that, the exact same thing. So basically I am just writing this thing equals to U tilde minus of pi. Here I just don't want to write it, that's why I'm not writing. Okay, and now so that will imply, if this is true, that will imply that U, capital U of x r comma t, this is equals to, now I want to divide it out by bk0 r. Okay, so if I divide it out, it becomes U tilde r t, okay, by beta k0 r. Okay, I have to be very careful here because there are lots of calculations going on. Okay, one sec, let me just clarify everything. Is minus this particular thing, beta k1 by beta k0 r u capital U r, okay, x r t, okay, and minus, it goes on, minus beta k minus 1 by beta 0 k r power k minus 1 r power k, and by r power k minus 1 capital U of x r t. Okay, so this is there. Now you see, if I want to write, if I want to find what is small u of xt, what is small u of xt? You see, small u of xt is limit capital U as r tends to 0. So basically I have to take limit r tends to 0, small r tends to 0. okay, of this particular thing, right? Then I will get small u, right? So let's just do that. So u of xt, okay, is limit r tends to 0, okay, this expression, okay, limit r tends to 0 both sides, the left hand side is this converges to u of xt as r tends to 0, and I just have to find out where this thing converges as r tends to 0. That's the question. Clear? Okay, so let's just do that part. So first thing first, so this is 1 by beta k0, this is always there, okay, and g tilde of t plus r, I'm just using that formula, okay, minus g tilde of t minus r by 2r, clear, plus 1 by, okay, so okay, let me again tell you what is happening. As limit r tends to 0, you do realize that all of this is gone, you know, because this things u r power k minus 1, these terms are there, these that are constant, those are constants, right? Okay, so as r tends to 0, definitely this I mean, or these expressions, remaining expressions are all gone. You are only left out with this particular thing, right, as r tends to 0. Okay, so limit r tends to 0, u tilde by b naught k r is equals to small u, right? So that's what I'm just writing. Okay, so now u tilde of rt is this, I mean u tilde of, where is it, u tilde of rt is this formula, where is it, you see this D'Alembert formula, right? I'm just using that thing, plus 1 by 2r. Sorry, it is a bit complicated, but I mean that's life, what can you do? Okay, so this is h tilde of y ty, right? Now this is equals to 1 by beta 0 k, okay, and of course you take r tends to 0 of this thing, what happens, this becomes g prime of t, of course tilde is there, okay, that's just the definition, yes, that's just the definition of the derivative, plus h tilde of t, clear, plus h tilde of t. You remember limit r tends to 0, the average of h tilde on this, I mean if you take the average of h tilde, that converges to h of t, right, the center. Okay, so this is how we are getting, and this is just the definition of derivative. Okay, so we have this. So therefore for n equals to 2k plus 1, okay, n equals to 2k plus 1, the representation formula which you are getting is this. So let me write it down. Okay, this is a little I mean, you know, big, but I mean that's the way it is. This is del t of 1 by t del t, okay, of n minus 3 by 2, okay, t to the power n minus 2, the average of del b xt g ds, okay, plus 1 by t del t of n minus 3 by 2 t to the power n minus 2 integral over del b xt h ds. Okay, so this is when n is odd, and gamma n is essentially 1, 3, 5, the you know product till n minus 2. Okay, x is in Rn and t positive. Clear? So what did we get? You see, u of xt is basically this thing, this b0k. How is this gamma n coming? You see, what is b0k? b0k, where is it? You see, b0k is 1, 3, 5 up to 2k minus 1. So that is what gamma n is here. That is what, where is it? Yeah, that is what gamma n is. Yeah, that's what I am just writing. And here, G tilde and H tilde we already know, right? G tilde, we have defined it to be, G tilde prime, where is it? See, we define G tilde somewhere, no? Yes, G tilde is defined by this. Okay, 1 by r del r k minus 1 of this, that the with respect to t, so del t of this particular thing, and again H tilde is given by this. I am just doing nothing but just putting everything together. Okay, and then I am using the definition of capital U, so I get everything in terms of small g and small h, and this is the formula. Okay, so let me emphasize this thing. At least I myself, in any of my courses on examinations, I am never going to ask you to remember this formula. Okay, this is just for your information, so that you know that there is an explicit formula which looks like this. Of course, whenever you need it, let's say in practical purposes, you can always consult your book. Okay, the purpose of doing this formula is basically to let you know that how this is derived. Okay, there is nothing special about it. Once you know how to do it for n equals to 1, you go from there to n equals to 3, and then you use the method of descent, Hadamard's method actually, okay, to go to n equals to 2. And here we are not doing anything but generalizing this fact. Okay, generalizing this fact. How are you generalizing it? So we are generalizing it in this way. We are just defining our new U tilde and H tilde and G tilde like this, and with this generalization we are exactly using the same sort of idea to prove what we want. Okay, the same idea. So the important thing is, the last week whatever the idea we have used, this idea. Okay, once you understand it, you can just replicate the same thing, but of course you have to have the specific, that particular form of capital U tilde, H tilde and G tilde. Fine, now you have this formula. Now what is the guarantee that this is the solution? Yeah, that is one thing. Yes, what is the guarantee? So for that, the existence theorem for wave equation in odd dimensions, okay. So basically we want to show that the formula which you obtained, let's call this as star, this formula, this formula which we have obtained, let's call this formula as star. We want to show that this formula is actually valid. Okay, so the theorem says that assume n is odd integer greater than equal 3, okay, and G is in Cm plus 1 Rn. Let's just assume that. Okay, H is in Cm Rn. Okay, see why we need a little more smoothness in G, because we want that G prime is involved here. You see, capital G prime and all this. So G has a derivative kind of thing involved. H does not have any derivative involved in D'Alembert. So that is why we always need a more more smoothness on G, yes, with respect to, and I mean in comparison to H. For M equals to n plus 1 by 2. Clear? Now define U by star. Okay, then the following is true. U, the capital, the small u which you are going to get is in C2 of Rn cross 0 infinity. Okay, so please realize this thing. This the regularity on G and H is not to get more regular u, but this is just to compensate the dimensions. Okay, so u is in C2. Number 2, is, of course, u satisfies the wave equation. So this theorem guarantees that the solution which you are getting with start, this solution, that is actually the original solution of the wave equation, the explicit solution in Rn cross 0 infinity, okay, and C limit xt going to x naught 0, x is in Rn, t positive, okay, u of xt, that is g at x naught. Clear? So basically what I am saying is u is such that it satisfies the boundary condition. Limit xt going to x naught 0, okay, ut of xt is h of x naught. Now I will actually ask you to do this, please. Yes, verify the C part, at least the C part, huh? I mean, it's not very difficult to see that. I mean, you just have to verify that that limit goes to G and this limit goes to H. That's all. Okay. So please do that part yourself. Okay. I'm not going to do that part. And of course, this is also, I mean, not a very difficult thing to do. Okay. The second part. The first is we have to check. But I mean, let's see. I mean, what we can do. So basically, the C part you have to do it yourself. Okay. Please check this part. Okay, so let's first of all find that whether u is C2 or not, and whether this satisfies this equation. See, if u is C2, if let's say u satisfies this equation, utt minus Laplacian of u equals to 0, I mean, of course that second derivative exists, yeah, and I mean, we have to just show that they are continuous. Okay, so let's do that. So proof. Now we are starting out with first letting that let g is identically equals to 0. Okay, so what is u of xt? This is just to make our life simpler. Okay, 1 by gamma n. See, if g is 0, this part is gone, that part is gone, right? So we are only left out with this. Okay, so 1 by gamma n, 1 by t del t of n minus 3 by 2 t power n minus 2, the average of h, right? Okay, so that, let us call that is, I mean, we call this average as h, right? Capital H. Okay, so this is 1 by t del t, okay, of n minus 3 by 2, okay, and t power n minus 2 capital H of x comma t. Yes, this is what we defined in the earlier weeks, if you remember. Yes, so that is always there, and then from I don't know what did I write, that lemma. Okay, lemma 2 1. Where is the lemma? Yeah, lemma 1 2. Sorry, 1 2. Okay. So this lemma 1 2 from lemma 1 2. Okay, what we have is utt. If you now write what is utt, that is what is 1 by gamma n. Okay, 1 by t del t of n minus 3 by 2. Okay, and then it is basically t power n minus 1 ht of x comma t. Okay, this is I'm using lemma 2 here. U, if it is something like this, utt is basically del t square of this whole thing. Okay, see, I mean, let us look at the first expression. You see, you just replace it by t here. Okay, if you just look at the whole expression, it is del 2 del t square 1 by t del t whole power k minus 1 t power 2k minus 1. Okay, h here, that is 1 by r del r whole power k. So here it will be r is t, essentially 1 by t del t of k r power 2k del phi del t. Okay, that is what I wrote here. Here I just replaced r by t here, so you see that is what it is written. Clear? Okay, so please don't get confused, this is exactly the same thing, I am just replacing r by t. Okay, so that is there. And now once you have this, okay, so you remember that what is capital H of t of x. If you remember, when we did that mean value property, here also we calculated in the first week we calculated this thing. H of t is t by n, the average of bxt Laplacian of h dy. Okay, I hope you remember this thing. So this calculation, if you forget it, please do it yourself, because this is from the mean value theorem from calculation of Laplace equations. Yeah, we did this thing, you remember, we first of all changed the variable, replaced this with a b01 ball, right, with the change of variable, then calculated the derivative with respect to t. Okay, then again came back and we had this formula. Okay, if you remember this thing, it is fine. If you don't remember this thing, please do this calculation. You will get to do, use this sort of calculation everywhere. Okay, so this is where we are using again. Okay, we see that h of t is there. Okay, so also let's put it like this. So u of tt is this, and h of t is given by this. Yeah, this I am not proving this thing. So this is from I did it twice actually. Once in the first part of wave equation, and once in the very beginning of Laplace equation, the same calculation was done. So I'm just I'm skipping this. Yes, so once you have all that, now I am just putting all of this together. See, utt is basically these particular things times ht. Ht is given by this, so I will just replace this thing. So therefore utt is 1 by n alpha n gamma n 1 by t del t of n minus 1 by 2, okay, integral bxt Laplacian of h dy. Okay, so that will actually give us 1 by n alpha n r power n, okay, 1 by t del t of, I am taking one derivative here. Okay, so n minus 3 by 2, okay, 1 by t, one derivative, so I am just breaking one from here. Okay, it will be del b xt Laplacian of h ds. Okay, I hope you remember the formulas which I taught you last in last few classes. What is the derivative del t of this particular thing? If you remember, del t of integral bxt Laplacian h, you don't have to have Laplacian of h, this can be any summable phi, so that is equals to del b xt phi, right, with respect to ds, of course, the surface integral, and this is dx. Okay, so that is there. Yeah, if you remember this formula, we did this few days back also, we did this formula. Yes, okay, I'm just using that formula. So 1 by t del t, I'm breaking it up, and one part I'm just using, this is 1 by t del t of integral over the boundary is the integral over the ball. That is what I'm just writing it down. Clear? Okay, fine. Now again what happens when Laplacian of capital H xt, if I calculate it, so basically that is Laplacian of integral del b 0t h of x plus y, okay, dsy. Clear? This delta is with respect to x. Okay, this delta is with respect to x. Okay, so what am I doing? Capital H is, if you remember, that's the average of small h, right? That's the average of small h. Now I'm just writing it down, and again taking a change of variable and shifting the origin to center to the origin. That's all. I'm not doing anything else, just that. Yeah. So capital H is the average of small h, yes, over the sphere del B with radius d. Now I am just replacing the center from x to 0. That's all. Yeah? So the change of variable. So this is essentially, if you write it down, that is del B xt Laplacian of h. Okay, I can just take this inside, right? Okay, because this integral is with respect to t. Okay, sorry, with respect to y. Okay, so and this is with respect to x. If you yeah, the delta is with respect to x. This integral is with respect to y. I'm doing. X is I just changed the variable. So you see, this del b initially was at the center x and time t. I just change the center to origin. Okay, so delta x of this particular thing. So that is why I can take the this derivative, the twice derivative with respect to x inside. Yeah, delta inside. So it becomes this ds. Clear? Now, of course, therefore, you can see that therefore u of tt, okay, u of tt equals to Laplacian of u in Rn cross 0 infinity, right? So if you have something like this, you can see that essentially you can see that utt is our this thing, right? And Laplacian of u, if you calculate, then what do you get? Laplacian of u is essentially your utt, yeah. So that is what I just proved it, yeah. That's what we just proved, that utt equals to Laplacian of u. That's what, yeah. So I hope that is clear, because see what why is okay. Let me explain to you how this is coming. Utt is essentially you have 1 by n alpha and r power n r to the power n, 1 by t del t of n minus 3 by 2. Okay, and of course you have this particular thing, right? Sorry, this is not r to the power n, this is gamma n. Yeah, I forgot. This is just by reflex I wrote it. It's gamma n. Okay, and this integral of Laplacian h. Okay, this now if you calculate what is Laplacian of capital H, that you can see that this is basically this Laplacian of small h, which is this term, right? So basically this particular term here, if you replace it by capital H, so utt is this whole thing, 1 by t times capital H. Okay, now you see what is u. U is particularly this thing. If you take Laplacian with respect to x of u, then that Laplacian will go inside, because this is with respect to t, this is with respect to t, it won't change, it will go inside and it become Laplacian of capital H. 1 by gamma n, 1 by t del t of n minus 3 by 2, all of this t to the power n minus 2, Laplacian of capital H. You see, that is what you are going to get. Okay, 1 by t del t 1 minus n minus 3 by 2, 1 by t Laplacian of capital H. Okay, so that is why utt equals to Laplacian of u. Okay, so that is there. Now of course similarly one can show that it works for if h is equivalent to 0. Okay, so initially I took g equivalent to 0 and I am showing that utt minus Laplacian u equals to 0. Again, you can do it in the same way by showing that h, if it is equivalent to 0, then the same thing happens. Yes. Now, how do you show that when both u and g and h are non-zero, then this is true? Okay, think about it. See, you can break this equation into two parts. One part is with g equals to 0, h non-zero. Another part is g non-zero, h 0. If you add those two up by the superposition principle, okay, then you get that this particular utt minus Laplacian u is going to be 0. Okay, So I hope that is clear. Okay. So, and of course this I asked you to do it yourself. So once you do it yourself, it will become clear. So I think we are going to end this video here, and it is more or less clear what we were trying to do. So in odd dimensions, this is the formula which we really need. This is our Kirchhoff's formula for n greater than equal 3, odd. Okay, n odd greater than equal 3, Kirchhoff's formula, and this formula actually solves our wave equation. Yeah, so let us end it here.